So let's move on to the next session of the day by Professor Allen, nanoparticles versus microparticles.
So we'll continue with the nanoscale, but this time we will check what are the properties which are changed when decreasing the size of mainly cellulose fibers down to the nanoscale. So some new properties appear, and because of these new properties, we can have some new applications. So, this is an introduction. Unexpected and attractive properties can be observed when decreasing the size of a material down to the nanoscale, and of course, cellulose is no exception to the rule. Cellulose nanomaterials exhibit specific outstanding properties and that we will see and are potentially useful for a large number of industrial applications. So after intensive research, several initiatives have emerged in the perspective of producing cellulose nanomaterial at large scale, was more or less what we mentioned previously, and a number of organizations have announced cellulose nanomaterial demonstration plan. These are the key players in the field of nanocellulose. So you can see that these companies are mainly from Scandinavia, so Norway or Finland, and from North America, so US or Canada, but also Japan. These countries have a strong background in pulp and paper industry, and so you probably know that the pulp and paper industry is not going so well, so meaning that they are looking for new opportunities, new market, and so nanocellulose is one of these. Another difference, but I don't know why, Scandinavian companies are mainly focusing on nanofibrils and North American companies mainly on nanocrystals. I don't know why, but it's like this. So regarding the properties of cellulose, there are some key intrinsic advantages of cellulose that we already mentioned. The high availability of the material, the renewability, it's a non-toxic material, it's biodegradable, biocompatibility, and the density is low. Some properties are impacted when decreasing the size of the material, like the specific surface area, the aspect ratio, the interactions among particles, the weight efficiency, gas diffusion, optical properties, mechanical properties, thermal properties, amphiphilic properties, and surface functionalization. So we review these different new properties in the nanoscale. We'll see how it is impacted and what can be the potential benefit and the potential application of these new properties. So first, the specific surface area. So it can be determined, as we mentioned just previously, by different techniques. It is a measure of the total surface energy per unit of mass. Typically, for cellulose fibers, the specific surface area is around 1 square meter or few square meter per gram. You see here the evolution of the specific surface area, considering cellulose nanorods as a function of the diameter. And you can see that, of course, it increases when decreasing the diameter of the nanorods. But what we can see also is that there is a huge increase below 20 nanometer. And cellulose nanocrystal, the diameter of cellulose nanocrystals is within this diameter range. So it means that we can have several hundred square meters per gram for the specific surface area. A first consequence of this is that when these nanoparticles are in suspension in water, of course, a lot of water molecules can interact with the surface. They interact, and of course, the mobility of these water molecules is reduced. And the consequence is this. We obtain a gel for a very dilute suspension, so here 2% of eucalyptus nanofibers in water. Another consequence is the increase, we have seen also this figure previously, the increase in the viscosity of the suspension, because the water molecules are immobilized at the surface of the nanoparticles. So this is the storage modulus of the viscosity as a function of the concentration, and we have this huge increase. Resulting applications, food, of course, can be used, the suspension can be used to control the viscosity of food. It can be used also in the cosmetic field, pharmaceutical industry, and of course in paint and coating. In paint and coating, what is interesting also is that this material or this dispersion have a shear sealing behavior, meaning that the paint can be easy to apply, and then the viscosity increase, meaning that it attached to the wall. Another consequence is the possibility to produce lightweight and highly porous foams or aerogel or cryogel, so it depends on the process which is used. In fact, the aqueous dispersion of cellulose nanofibers, for example, can be freeze-dry to remove water without collapsing the nanofibrils. And so we obtain this kind of cryogel that can be that can have a very low density. In fact, it depends on the liquid medium. If it's water, it can be a mixture of water and acetone and so on. It changes the porosity. But you can see that in some case, the density is very low, 7 kilograms per cubic meter. And of course, it can lead to application for porous templates, but also for filtration. This cryogel can be functionalized. So it means that a chemical modification can be performed, we'll see this on the right, or we can attach different particles. For example, in this case, cobalt ferrite nanoparticles have been attached to the surface of the nanofibrils, a different percentage, leading to an aerogel with magnetic properties. We'll have another example in the other slide with different particles that can be attached, but the possible application are for microfluidic devices and electronic actuators. On the right side, you can see cryogel or aerogel. In fact, cryogel is used when liquid nitrogen is used to produce these foams. Unmodified, so it's pure cellulose, and in this case, it was modified using a silane agent, meaning that the foam or the cryogel is more hydrophobic. When dropping water or an oil, in this case dodecan, on the surface on the unmodified aerogel, we can see that both liquids are absorbed. For the modified cryogel, you can see that only oil is absorbed and water cannot penetrate in the aerogel because of its hydrophobicity. And then when dropping these two different aerogel in a mixture of dodecan and water, so dodecan is in red here to see the oil phase. For the unmodified sample, both liquids are absorbed, and you can see that the aerogel lost its form. In the case of the modified aerogel, we have a selective absorption of the oil phase. And you can see that the material keeps in its form, meaning that it can be reused. And of course, possible resulting applications are for the selective oil absorption or also for oil spill treatment. Yes, so this is another application of the cryogel. So it was performed by quite recently by one of my Chinese PhD students. So first, he used cellulose nanocrystals, and these cellulose nanocrystals have been cationized to have a positive charge. He also used tempo-oxidized nanofibrils with negative charge and so we'll have some interaction, of course, and carbon nanotubes. And he also used sodium alginate, which is negatively charged. And he mixed these different elements, and then by freeze drying, he can obtain an aerogel that contains all these elements. So we can see from this zeta potential measurement the interaction between the different elements because cationized carbon nanocrystals are positively charged and most of the other elements are negatively charged. And so it leads to some stabilization of carbon nanotubes. You can see here, this is a dispersion just after stirring of 24 hours later. I realized, yes, sorry, it is here. This is for tempoxidide cellulose nanofibrils. You can see that the suspension is stable in water. Carbon nanotubes, not stable. It's not stable. We observe a sedimentation. And when mixing tempoxidized cellulose nanofibrils and carbon nanotubes, we can see that we can promote the dispersion of carbon nanotubes. So this is just the aspect of the cryogel, the pure cryogel, and here with 0.22 or 0.89% carbon nanotubes. So, of course, these nanotubes, these carbon nanotubes, give some conductive properties to the material. You can see the evolution of the conductivity as a function of the carbon nanotube content. And also, so we don't discuss this too much, but it improves the mechanical properties. For example, we can, with our tensile test, but here we can see the toughness of the material. The toughness corresponds to the area under the stress strain curve. And it determines also, maybe I will discuss this, the specific modulus as a function of density with a comparison with other systems. And of course, what is interesting is this kind of system is to have a high modulus and a low density. And you can see that we perform quite well compared to other systems. So the objective, in fact, of this work was to obtain electromagnetic interference shielding material. And so for this, it determined here, you can see the specific electromagnetic interference shielding efficiency as a function of the density for the system he developed and compared to the other system. And again, it performed quite well. So the aspect ratio. The aspect ratio is also an important parameter, mainly for composite application. You have here cellulose nanocrystals obtained from different sources of cellulose. Remember that the aspect ratio of cellulose nanocrystals mainly depend on the source of cellulose and acid hydrolysis condition. You can see that it can vary from about 10. So the aspect ratio is the ratio of the length of the nanorods divided by the diameter, from 10 to about 100. So for different sources of cellulose. Maybe you don't know this one, Capim dorado, or maybe this one, tunicate. Tunicate is this sea animal. You can eat it. I try. I don't like very much, but you can eat it. Capim dourado, you cannot eat. Capim dourado is a Portuguese name, meaning golden grass. And you can see why it is golden grass. So it's a very specific biomass that can find only in the Tocantins, which is a specific part in Amazonia. But it's used for jewelry and for handicrafts and so on in Brazil. I cannot go to the next slide. So another consequence when decreasing the size of the nanoparticle is that the average distance between the particle decreases as the size decreases, meaning that we can expect interactions between the particles and we'll see later that this can be important. Nanoparticles are weight efficient, meaning that we can improve properties for low filler content without detrimental effect on impact resistance and plastic deformation. For this, of course, it's necessary to have a good dispersion of the nanoparticle, and this can be a crucial step, a key step. What is the meaning of this? In fact, to have a reinforcing effect in composites or biocomposites, it's generally necessary to use around 30% fibers to significantly have an improvement in the modulus of the material. Of course, when increasing the stiffness of the material, the ductility decreases, meaning that the elongation at break decreases. The material becomes more brittle. When using nanoparticles, usually only few percent of this nanoparticle is necessary to significantly improve the stiffness of the material. So it's typically less than 5%, meaning that there is a big amount of matrix that provides the ductility to the material, meaning that the elongation at break remains quite high. Reduction of gas diffusion, it's called the barrier effect. We have seen previously in the video that when adding mainly crystalline nanoparticle in a polymeric matrix, we can induce a tortuous path for the gas molecule, and so it limits the diffusion of the gas, and of course it can be used, for example, for packaging application to limit the transmission of water vapor or oxygen or other gas. This is a different example in which the substrate was paper or cardboard. I don't remember exactly. Yeah, it was paper, sorry. And this paper was coated with different amounts of cellulose nanofibrils. And the air permeability, or air permeability was measured as a function of the amount of nanofibrils on the surface. We can see this decrease because, of course, when coating the paper with the nanofibrils, it's possible to fill the voids between the fibers. So these nanoparticles can be dispersed in the matrix to provide mechanical properties, or it can be also coated on the surface of a substrate that can be a polymer, but also paperboard. We can add a layer of cellulose nanocrystals or nanofibril to improve the barrier properties, but of course, the material is highly sensitive to water, and the permeability to oxygen will be increased in a high relative humidity condition. To avoid this, generally, another layer of a hydrophobic polymer, so polylactic acid in this case, can be added. So these are some examples of barrier properties. So it's slightly different. In this case, it consists of starch nanocrystals, and the matrix was natural rubber. For different starch nanocrystals content, the water vapor transmission rate was determined, the diffusion coefficient of oxygen, the permeability of coefficient of oxygen, and the solubility of oxygen. So what we can see here is that when adding starch nanocrystal to the natural rubber matrix, there is a reduction in the diffusion of oxygen. Okay? The permeability coefficient, maybe you can see there is a reduction in this parameter, which was expected because of the tortuous path imposed by the starch nanocrystals. But you can see also that the water vapor transmission rate was reduced, and this was not really expected because natural rubber is quite hydrophobic. Hydrophilic nanoparticles are added, and it reduces the diffusion of water vapor. On the right side, you can see an example in which nanocellulose composite with bismuth complex have been prepared, and it can inhibit the growth of bacteria and fungi. You can see here the zone of inhibition as a function of the percentage of bismuth loading. So it was for different bacteria and fungi, and we can see that this zone of inhibition increases, meaning that we can think about application for active packaging. Now regarding the optical properties. Small particles are invisible. Not really. But you know that when the size of the particle is below the wavelength of visible light, we cannot see these particles. So it means that transparent coatings or transparent films can be obtained. It can be for nanopaper. We have seen previously that it's possible to prepare nanopaper just by a casting evaporation process using a dispersion of cellulose nanofibrils or other nanoparticles. This nanopaper can be transparent. It depends on the drying condition and on the process. You have an example here in which this suspension has been freeze-dried. The material is opaque, which is quite normal. We've seen previously that this material is porous. And because of this porosity, the material is opaque. To remove this porosity, it's possible to hot press the material. This material is obtained. It's more transparent, but it's not really transparent. The reason is that there are some scattering of light, due to the surface roughness. To remove this surface roughness, a polishing treatment has been applied. And you can see that a transparent nanopaper is obtained. So this material is made of only cellulose and it is transparent. Also, so this nanoparticle can be mixed with a transparent polymer as matrix. Transparent polymer means amorphous polymer. And we can keep the transparency of the material. You have one example here in which an acrylic resin was used. It was mixed with 60% cellulose nanofiber. In this case, it was bacterial cellulose nanofibers. And you can see that the material retains the transparency. Same thing here with 5% bacterial cellulose nanofibers. The material is still transparent, but the mechanical properties are improved. So this is another specificity regarding the optical properties, but which only concern nanoparticles in the form of nanorods, meaning cellulose nanocrystals or chitin nanocrystals. This is called the chiral nematic behavior or iridescence. In fact, when the dispersion of chitin or cellulose nanocrystals is observed in polarized light, we observe this color domain here, which is called the birefringence. And this birefringence results from a local alignment of the nanorods, which is explained here. In fact, when using a dilute suspension, we have an isotropic phase, meaning that there is a random orientation of the nanorods. From a given concentration that depends mainly on the aspect ratio of the nanorods, we have some organization or self-assembly of this nanoparticle, leading to what is called an isotropic phase or chiral nematic structure. This phase, which is observed here, consists of an alignment of the nanorods in a given plane of the suspension, and then for the upper plane, we have an orientation, but with a shift in the orientation of the nanorods, and so on. And when we recover the same orientation, this distance is called the pitch of the dispersion. Okay, so it's the pitch of the helical structure. And this organization can be can be preserved when evaporating water. But it's necessary to proceed to a slow evaporation, and we can obtain film, nanocellulose films, with some coloration. And this coloration refers to this wavelength here. You can see that it is linked to the pitch of the dispersion, and this pitch can be controlled, for example, by adding some electrolyte to the suspension. We can decrease the pitch of the dispersion, meaning that we can adjust or tailor the wavelength of the light, and it depends also on the angle of observation of the film. And so, this pitch can be controlled through the ionic strength. It can be controlled by temperature, by the concentration, by the exposure to magnetic field or ultrasonic treatment. You can see here a suspension that has been treated using an ultrasonic treatment with different energies, and it changes the color of the film. I like this figure, this picture here. So it's a mixture of confetti that were cut from cellulose nanocrystal film, prepared with different electrolyte concentration. They change the pitch and then the color. And so we obtain these different colors. This is also found in nature. It's slightly different, so it's not cellulose. It's mainly collagen nanocrystals or nanofibers, which can be found in the shell of a beetle, some butterflies like morpho, but also in some plants, as it is reported here. And so the possible applications are for security paper, UV or IR reflective barrier. So this is also an interesting example of the use of this chiral nematic order. Photonic, mesoporous, inorganic, so it was silica, solid, were prepared, and they were cast, a cast of a chiral nematic liquid crystal, which was formed by cellulose nanocrystals. So the cellulose nanocrystals were organized, we have this self-assembly. Silica was formed in the presence of the cellulose nanocrystals, and then by a treatment at high temperature, cellulose was burned, and we keep only the organized porosity of the silica film. And you can see that depending on the organization of the nanocrystals, we can have silica films with different colors. And when this film is immersed in water, so water fills the porosity, the color is lost, but it can be recovered by drying. So now regarding the mechanical properties. So cellulose nanomaterials contain only a small number of defects. The actual Young modulus is close to the one derived from theoretical chemistry. Here you can see the tensile modulus that has been reported in different papers. It was obtained experimentally, or it was obtained by calculation. And you can see that there is a broad range of values, of course. The first experimental determination of the modulus of cellulose crystals was reported in 1962, so it was quite a long time ago, by a Japanese group. They performed a tensile test on a rami fiber. So rami is a highly crystalline cellulose fiber. And so they performed this tensile test, and at the same time, they record the X-ray diffraction pattern. Meaning that from the X-ray diffraction pattern that can have the variation of the dimension of the crystal, and from the tensile test, they can obtain the force which is applied to the material. And of course, from this, they can determine the stress-strain curves, and then the modulus of the crystal. And they found a value that was 130 gigapascal. Under 30 gigapascal is the average value which is obtained in the literature. Remember, for cellulose nanofibril, it's slightly lower, 100 gigapascal, because of amorphous domains. Of course, this is important for composite application. This paper is also interesting. In fact, they determine the optimal dimensions of cellulose nanocrystals to obtain the optimal fracture energy of, in this case, 1 beta cellulose nanocrystal. So 1 beta cellulose nanocrystal extract from trees. And from the simulation, they found that the optimal dimension are this one. And it exactly corresponds to what is found in trees. So it means that nature has already optimized the mechanical properties, in this case the fracture energy, of cellulose. So cellulose or other polysaccharides are lightweight material. And so it means, do you remember in the video it was explained that cellulose nanomaterial modulus is potentially stronger than steel. You have here a table in which you have different materials, so glass, Kevlar, steel, cellulose nanofibril, cellulose nanocrystal, the corresponding modulus, the density. So for crystalline cellulose, it's between 1.5 and 1.6, and the specific modulus, which is a ratio of the modulus divided by the density. And so what you can see is that for cellulose nanomaterial, this specific modulus is higher than for steel or for glass, and in the same range as Kevlar. And this is important for composite application because it's necessary to use reinforcement with a high modulus, but the density should be low also. So thermal properties. When preparing a cellulose nanomaterial film, it is observed that the thermal expansion coefficient is very low. This is explained by the high crystallinity of the nanoparticles, but also by the strength of the cellulose nanomaterial network interaction. So, of course, we have some hydrogen bonding between these nanoparticles. And this property can be used to reduce the thermal expansion coefficient of polymer nanocomposite when you're mixing this nanoparticle with a polymer, if the strength of the network, of course, is strong enough to restrict or to limit the thermal expansion of the matrix. I have one example, which is here. This is the thermal expansivity as a function of temperature for cellulose acetate, which was the matrix, and for a nanopaper, so I don't remember, I think it was, yes, it was tempo oxidized cellulose nanofibril, so I don't remember the origin of cellulose, but it's not very important. So the thermal expansion coefficient that corresponds to the slope of the curve is very low. It's much higher for cellulose acetate, and for the composite containing 2.5% cellulose nanofibril, you can see that we have a reduction in the thermal expansion coefficient. Amphiphilic properties. In fact, when considering cellulose nanocrystals, but the same for nanofibrils, we have a mainly crystalline material, meaning that we have some non-polar surface, which are rich in CH groups, and polar surface, which are rich in hydroxyl groups, meaning that we have a difference in polarity. This is similar to what is obtained for surfactant. Surfactant molecule, we have a polar head and a hydrophobic or apolar tail. And you know that this surfactant can be used, for example, to stabilize emulsion of oil in water. And it's possible to have the same effect, but using solid nanoparticles. This kind of emulsion is called Pickering emulsion. Okay, and you understand it's possible to use these nanoparticles. You have one example here. that consists of styrene, which was the oil, Pickering emulsion stabilized by cellulose nanocrystals. So on the left side, maybe we can check here, it's a confocal laser SEM of droplet stabilized by CNC with double staining. So it was cellulose and hexadecan was stained with a different component. We can see here the SEM observation, so the droplet of oil, and we can see the cellulose nanocrystals on the surface of this droplet. And of course, the possible application is for Pickering emulsion or detergent and so on. Surface functionalization. You already know that I'm not a chemist, but chemistry of alcohol is well known, and there are many possibilities to graft different molecules on the surface of cellulose fibers or natural fibers, but also, of course, this cellulose or starch or chitin nanoparticles. But the effect of this chemical modification is even more important because of the increase in the specific surface area. And so there are different options, which are reported here. So it's possible to substitute the OH groups from the surface with different kinds of small molecules to limit the hydrophilicity or increase the hydrophobicity or to provide some functionalities to these particles. It's also possible to graft longer molecules or macromolecules. And for this, there are mainly two options, which are reported here. The grafting onto approach, it consists in directly grafting existing macromolecules on the surface of the nanoparticles. Or grafting from strategy that consists in initiating the polymerization at the surface of the nanoparticles. And so the macromolecules are directly grown on the surface of these nanoparticles. So, I briefly present some new properties resulting from the reduction of the size of cellulose or starch or chitin down to the nanoscale. And these are the main sectors or markets which are impacted by these new properties, and some already exist. So I show just previously to Raju and Uni a pen in which cellulose nanofibrils are used in the ink, and the writing is very smooth. This is developed by Mitsubishi in Japan, but there are some other applications. So just a brief conclusion. Cellulose nanomaterial exhibits the intrinsic properties of cellulose: renewability, non-toxicity, biodegradability, biocompatibility, low density. And when transforming this material down to the nanoscale, new properties can be found, like increased specific surface area and ensuing greater impact of surface functionalization, high aspect ratio, enhanced mechanical, thermal, rheological, optical, and barrier properties. And so, of course, these new and outstanding properties give cellulose many industrial or new industrial applications in different sectors. Thank you very much for your attention. And so if you have any question.
This session is open for questions.
Yeah, Professor, so I have seen one images where you have mentioned about transparent film made out of acrylic resins.
Yes?
So, I believe this kind of application targeting on electronic industries.
Yes, I'm sorry, yes, I didn't mention the possible applications. I'm sorry. Usually I try to check. Yes, the applications are for electronics,
Yeah.
for flexible circuit or energy solar panels.
So how do you disperse these nanomaterials into the acrylic resin? So What is the conventional method of doing this?
Yeah, yeah, this is a good question. I don't know. You can see that it's not one of my paper, one of my work. It was developed by colleagues in Japan. And I have to say that I don't remember how they disperse the nanofibers. I don't remember. I'm sorry.
No, because generally, what I understand, acrylic resin is very high viscous material, so
Yeah.
dispersing the cellulose
It's
may be
difficult.
very difficult and
Yes, 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 yes. I don't remember. Maybe it was, I'm not sure. Because it can be an impregnation process. Maybe with 60%, they can prepare a mat of cellulose nanofibers that can be impregnated with acrylic resin. I'm not sure. I have to check the paper, but
okay. Thank you, thank you.
More questions?
So like you talked about like cellulose nanorods, cellulose nanofiber and microfibers. So like the extraction procedure involves like, so I think like in case of nanorods, you do acid treatment to remove all the amorphous regions.
exactly.
In case of nanofibers, you just use like hydrogen peroxide and sodium.
No, no, no. It's a mechanical treatment.
Okay.
It's a mechanical treatment because cellulose fibers consist of aggregate cellulose nanofibers. So it's necessary to separate these nanofibers. And the treatment you mentioned can be used to facilitate the process.
Okay.
It's just a pre-treatment.
Like the thing is like, like I understand, like I also use cellulose fibers as a sustainable material to make some biocomposites, but the extraction procedure requires using a lot of like very heavy chemicals or mechanical energy, which itself again
Yes.
like needs more energy and so on.
Yes,
What's
yes.
a sustainable way of extracting these?
No, for sure. For sure it is not. And even when using chemical pre-treatment, you have to be care about the pre-treatment. Because if it's not a green pre-treatment, of course, the resulting material will not be. Yeah.
So we are trying to figure
Meaning
out
that probably enzymatic pre-treatment is greener.
like enzymatic or like
Yeah, exactly. Yeah.
So, just a question out of curiosity. Can we bring in shape memory properties into carbon nanofibers?
In carbon nanofibers,
Cellulose nanofibers.
yeah, so yes, I understand cellulose. I said the carbon, but cellulose, I don't know. I don't know. Maybe there are some paper on this. I don't know. You know, the increase in the number on nanocellulose, if you are working on nanocellulose, you probably know that there is a lot of literature. And so, just one comment. You maybe know that I have published a book on nanocellulose in 2012. And then the publisher asked me, after a few years, to publish a second edition. It was in 2017. And it was a lot of work because in 5 years, the number of papers on nanocellulose increased a lot. And recently, so it was last year, in fact, during the SAS meeting that was in New Orleans last year, the publisher asked me the third edition. And I said no. I said no because the book is already 650 pages. I will not add more pages, but I have some comments from colleagues, and so I'm working on a textbook that will be much shorter, but that will be more for students and for companies also, with just the basic principle. But so sorry, it was just a comment. Yes, so it means that I don't know because I have to review many papers for these books, of course. I didn't see anything on shape memory effect, but maybe there are so many papers I don't know.
Thank you, sir.
Complement that, these cellulose particles are being distributed in some matrices which are matching memory effect. Means that memory effect can be modeled, but in fact you can disperse it in a suitable matrix, and the shape memory can be modulated based on the interaction between the cellulose particles and the matrix. The different research articles are readily available. So I think the research scholars can support you in that. So it's a very good question. Thank you.
And sorry, maybe I have a comment I was thinking about. Because you mean for only cellulose nanomaterial, memory effect for on. Yes, I think it's probably difficult, but I had a Chinese PhD student that came for 1 year in Grenoble that was working on this kind of material, but it was not only cellulose nanofibrils. It was mixed with chitosan and another polymer, and he had very interesting results. In fact, when he immersed his material, I can give you the reference if you are interested. When he immersed this film in water, it can move on different shape, in fact, depending on the orientation of the nanofibrils. And when he put this material, I don't remember in which liquid, he recovers the former form, which is a shape memory effect. But it's not only cellulose nanofibrils, it was with chitosan, it was also with polyvinyl alcohol. I don't remember. So it was the main ingredient, let's say, but it was a very nice work.
Questions?
Professor, you mentioned one technique, Japanese techniques regarding that XRD and tensile together you are doing. I mean, to find the modulus, right? It is
Sorry, which
the
technique?
tensile testing along with the XRD.
Tensile testing?
Yeah. In your previous slide.
I think I mentioned tensile testing only when
Simultaneously XRD along with some Japanese peppers eventually, yeah.
Yes. It was not really a slide. Yes, here. Yes,
So,
with the rami fibers.
okay, what exactly we can get from this testing? Actually, I didn't get modulus. For getting the modulus, we are using this one.
In this work, they determine the modulus just of the crystalline part of cellulose.
Okay.
And this is difficult to determine because the crystalline part is embedded in amorphous domains. So meaning that when you perform a tensile test on a fiber, so first it is difficult to perform it on a single fiber, but if you can do it, you have the modulus of both the amorphous domains and the crystalline domains. The interest in what they perform is that they record X-ray diffraction pattern during the tensile test, meaning that they can have, and the signal which is obtained by X-ray diffraction come only from the crystalline domains. So it means that they can determine the strain or the deformation of the crystalline part of the material. But of course, the force which is applied on both the crystalline and the amorphous domain, meaning that they have the force applied to the crystalline domain, they have the deformation of the crystalline domain, so meaning that they can plot the stress-strain curve of the crystalline domain, and then the modulus.
Okay. Thank you.
Sir, can I ask one question?
Yeah?
Sir, which instrument is
Can you come closer because it's difficult to hear? And
Sir, which instrument is used?
the microphone is not working. No? Okay.
Which instrument is used to measure this? Because it's narrow size now. We can't
To determine this modulus, I don't remember exactly the detail. So for modelization, so it can be different model. I'm not expert in this. For the experimental determination, different techniques have been used. So I mentioned the previous one, tensile test and X-ray diffraction. It can be also AFM, like here. You can perform a three-point bending test on the cellulose nanocrystals. It was also obtained from Raman spectroscopy. Raman. Raman, okay. It's an Indian guy. Yes, Raman spectroscopy. So I don't remember exactly the details, but when submitting the material to tensile test, there is a shift of some bonds. And from this shift, you can determine the modulus of the material. And I don't know if there are some these are the main experimental techniques. I'm looking, you can see the paper is quite old, but these are the main experimental techniques. But of course, it's difficult to determine from just a tensile test. Yes. Oh, it's impossible, in fact. Not only difficult.
One last question. So, the surface modifications that you showed.
Yeah.
So, like in most of these biocomposites or like any composites, the failure tends to, or like one of the main failure mechanism is the interface between these two different materials could be the site where the failure could
Yes,
be
that's the
initiated.
critical point.
Like,
Yes.
so I think like you showed a lot of interesting like surface modifications that are like you can functionalize the cellulose so that the interaction between the cellulose and the like
the matrix.
matrix could be improved by this like functionalization.
Yes.
And like a lot of these like you showed were all like organic modification actually. Like what happens like in case of like inorganic like so currently we are working on a project where we are trying to improve CO2 capture
Yeah.
by using cellulose dissolved in NaOH. I mean, it's been already done and published in some research. So when cellulose is added, it also, in addition to absorption by NaOH, there's also adsorption of CO2 on the surface of cellulose, which increases the amount of cellulose that is captured. Usually this happens as calcite crystals on the surface of cellulose. Like how this could be, how can we like, use this to improve the interfacial stability with the matrix? Like, do you have any?
In fact, there are different options. You can graft small molecules. The result is just that the surface of cellulose is hydrophobized. Okay. But you can also, I mentioned, graft longer macromolecules. And in this case, you can have stronger interface or interphase. Because if the graft macromolecule is the same as the molecule which are used, or macromolecule used for the matrix, we can expect some entanglements. And there is another thing. If this molecule or macromolecule or this polymer is semi-crystalline, we can expect some co-crystallization between the graft molecules and the molecule from the surface. And so it improves the strength of the interface.